Okay, hi year 12. We are starting our next topic, and our next topic is curve sketching using the derivative. So it follows on from our curve sketching without using the derivative. So using your booklet, scroll down to the first section, 3A, we're going to be looking at increasing, decreasing, and stationary at a point. Okay, so we still want to, where possible, understand what's happening by looking at the graph. But what we're going to be looking at is finding the first derivative, and that will tell us how that links to what the graph is doing. So remembering that dy dx is the same as f dash of x. So I'll be interchanging between f dash and dy dx. Here we've got f dash of a, that's our first derivative, f dash of x at a point x is equal to a. If you remember, that's what that was from year 11. Okay, so let's go through our parts in the boxes. The first part says that if f dash of a is greater than or equal to 0, then the function is called increasing at that point. And that would be happening down here where point A is and here where point G is. So the function is increasing in this part of our curve through A and through G. If I took the derivative at that point, I would get an f dash or a dy dx greater than 0. So that's written the same over here. So dy dx is greater than 0 at that point, it would be increasing. And we'll show you that in an example soon. Similarly, if I find f dash of a and it's less than 0, then the function is called decreasing at that point. And if you have a look at the curve down here, that would be at the point C. That would also be at the point E, because our curve is going downwards and decreasing. It would also be at the point I. Our curve is decreasing along there. So if I was to take the derivative of the function at those points, I would find that my f dash of a would be less than 0. And that's this one here. Would also be saying dy dx is less than 0 and it's decreasing. If our f dash of a is equal to 0, then our function is called a stationary point. We looked at those last term. They were our most important ones last term. I guess in remembering with all of this, when we're taking f dash of a, our f dash of a, well, I'll just write that down, I might just call it f dash of x. F dash of x and dy dx are our first derivative, and that's our gradient of the tangent. So what we're looking at all these points is the gradient at that point that we're talking about. Okay, that's the main thing to remember. Is we are talking about the curve, but in essence we're actually talking about what happens to the gradient at that curve, at that point. So a stationary point, we would have a 0 gradient. And remember, f dash, our first derivative, equal to 0. That would happen here at point B. That would also happen at point D. There's a little one in there. It would happen at F. And it would happen at H. The gradients of all those tangents at that point would be equal to 0. And we call that stationary. Okay. If f dash of x is greater than 0 for all x, then the curve is always increasing, and we call it monotonic increasing. If f dash of x is less than 0 for all x, the curve is also always decreasing, and we call it monotonic decreasing. Let's have a look at the examples below. Okay. The first example says find all x values for which the curve f of x is equal to x squared minus 4x plus 3 is increasing. So when a curve is increasing, we're knowing that the tangent at the points that it is increasing is greater than 0. So f dash of x is greater than 0. So that's what we want to find. So f dash of x is our first derivative. It's dy dx. We just differentiate this function here. And we get 2x minus 4. And it's increasing when it is greater than 0. So we're just going to solve this inequation here. That would become 2x is greater than 4. Remembering, I'm adding 4 to both sides here. We don't need to flip any signs or anything like that. Now I'm going to divide by 2. So x is going to be greater than 2. So our curve is increasing when x is greater than 2. Now what I've done below is drawn a little sketch of that. So I found the zeros of this function here. By factorising, the zeros were at 3 and 1, so I could quickly draw that function. And when I drew that, oops, I'll just fix that up for us. Okay, that's That's a little bit better. When I drew that function there, what I ended up with was it cut the x-axis at 1 and 3. And what we know is that our turning point, or our stationary point, is going to be halfway between those two zeros on a parabola, and that's at 2. So our stationary point happens at x equals 2. So our curve is not increasing at x equals 2, but points to the right of that. So any points greater than 2 is increasing, and that's what this is telling us up here. So we can trust that works. Okay, let's look at the second one. Our second example. Find the stationary points on this parabola. Okay, so remember the stationary points from our information up above are saying that I might just use dy dx this time. Same thing as f dash of x. That equals 0. So this is where our tangent at the curve is flat. Okay, so let's just find what dy dx is. Dy dx is going to be 2x plus 6. Where is that equal to 0? 2x will be equal to minus 6, and x will be equal to minus 3. So I just want to quickly draw that, and that will be between our two zeros. If I factorize my original function, I'm looking for numbers that will add to 6, multiply to 5. That will be 5 and 1. So our zeros are at minus 5 and minus 1. So if I was to draw that there and there, that's our parabola through here. We're saying that our stationary point is at x is equal to minus 3. If you think what number is between minus 5 and minus 1, it is minus 3. So yeah, we're pretty good. We're spot on. Our stationary point happens when x is equal to minus 3. And we can find the other value, because it says what's the stationary point, not just the x value. So we know that minus 3 is where the stationary point happens, but what's y going to be equal to minus 3? Substitute x equals minus 3 back into our function. Y is going to be equal to minus 3 squared plus 6 times minus 3 plus 5, which is 9, minus 6 1 6 12 6 3 is 18 plus 5. Pop that in your calculator or your head, you get minus 4. So minus 3 minus 4 is our stationary point there. Okay, let's go and have a look at the next question. Going down to number 2. Find any stationary points on the curve y is equal to x cubed plus 4x squared minus 3x minus 1. So very similar to the last question. Let's go dy dx. And that is equal to 3x squared plus 8x minus 3. Stationary points are happening when dy dx is equal to 0. So remember, you can either remember that, but I want you to understand why we're doing that. It's when the tangent at our first derivative has a 0 gradient. So our curve is flat. Not our curve is flat, but our gradient of the tangent at that curve's point is flat. And that's what we want to be looking at. So dy dx is equal to 0. We need to work out when dy dx is equal to 0. So 3x squared plus 8x minus 3 is equal to 0. So if you want to pause the video and have a go at that, let's see if we can get it into our factorized form. What are we looking for? Adding to 8, multiplying to minus 9. What are we going to have? We're going to have 9 and minus 1, because 9 times minus 1 is minus 9. 9 minus 1 is 8. Pop the 3 into that bracket there, and we're going to end up with x plus 3 and 3x minus 1 equals 0. Stationary points, remember, we need a point. Let's find what our x values are, setting each of those to 0. X is going to be equal to minus 3, and x is going to be equal to 1/3. We can then find our y coordinates that go with that as well. So if we substitute each of these x's into here, we'll get our actual stationary point. Okay, so let's have a look at example number 3 now. And what we are doing is showing that this function, x cubed plus x minus 1, is always increasing. So if you have a look at what the notes at the top are saying, that's when our f dash of x, or dy dx, is always greater than or equal to 0. So we want to be able to show that. So let's just differentiate and see what we come up with. So f dash of x is 3x squared plus 1. And we want to show where that is always greater than or equal to 0. Now, let's think about that. There's a couple of ways to think about it. If I was to graph that, that would look something like, approximately, something like that. If you think of it like that, if we were to graph it, all our values of our function for each x value are always going to be greater than 0 because we're sitting above the x-axis. If we were to find the discriminant, we'd find that our discriminant was telling us the same thing. But in this case, you can also think of it as, with this function, you might write a little sentence or something like that for it. If I was to pop in 0 in x, I'd get 1, which is greater than 0. If I was to pop in any value of x bigger than 0, so 1, 2, 3, or 4, or 5, I'd be squaring it, timesing it by 3 and adding 1, so it would be greater than 0. Any value less than 0, which is a negative value of x, I'd be squaring that, so the negative would disappear, timesing it by 3 and adding 1. So no matter what my value x is, so no matter what x value I have, I get a value of f dash of x that's going to be greater than or equal to 0. You can see my graph and you can write a little sentence in there. There's no use trying to solve that equation. It's going to end up with an inequality and trying to square root a negative number that's not going to happen. But we could bring the discriminant in there as well if we wanted to. That should be enough information to get you guys through the first example. Not the first example, the first exercise, which is 3A.